So continuing with Module 12, talking about forecasting, there is a very simple procedural setup that we follow when we're doing any type of informational forecast, and it's the scientific method. And so once we receive the data, and we've just talked about how we would receive the data and the different types of data that we could receive, the variety of numerical models that we would receive can then be analyzed into a set of phases. And the analysis phase consists of data is used to create current states of the atmosphere. The data is converted into uniform initial values, and then those values are both horizontal and vertical conditions. So that means that I'm looking at both the surface and what's going on in the upper atmosphere, because at this point in the semester, if we haven't figured out that everything that's going on in the troposphere counts, we haven't learned anything, right? So we need to know what's going on in the uppermost parts of the atmosphere, of the troposphere, all the way down to the surface on its condition. As far as the prediction phases of numerical modeling, there's basically a governance of equations, and we've already worked with these throughout the semester. So we're just reiterating what we are already doing. As far as once we have those numerical modeling, we can then do post-processing phase, and this is where I create models and statistical models on that information. Right, and so here's a little bit of that numerical modeling. So I have my numbers, and now I'm turning them into outlooks of information. Different types of forecasts are put on different ranges, and other than our daily forecast, which is our day-to-day, we can do what's called a medium range forecast, and this is something that gives me 72 hours to even the full week to a few weeks in advance, and that gives me kind of an outlook of what I can predict or see coming in the near distant future, right? So that gives me kind of like, if I look today, what is going on next Saturday, for example. This tends to work really well, but obviously it's subject to change, and there's a lot of inaccuracy when I'm trying to predict for one region that far out in the future. But here's an example of medium range forecasts. Long range forecasts or seasonal outlooks, this is looking at the entire season, so like a 3-month clip it, and saying things like, it seems like this season will be dry. So I will say we are going to be within drought this summer season, for example, on there. And so here's long range forecasts. Surface maps, this is one of the predictive models and how I put that information into visual, right? And so here is a visual surface map, and these are my different data points. And once again, when I'm looking at it, so this is a weather station, the top number is the actual temperature, and the bottom number is the dew point temperature. The dot itself shows me the amount of cloud cover in a given location, and if there's a little stem on it, it's telling me where the wind is coming from. It's pointing to where the wind is coming from, so I would be able to name the wind. So for example, where my little arrow here, I can see that the wind is coming kind of in the northeast, so I would say this is a northeasterly wind, which is unusual because we know that everything in this region tends to be westerly, so they're coming from the west going to the east. This one's coming from the northeast in that because there's a little stick, but there is no cloud cover. The current temperature is 22 degrees and the dew point temperature is 10. So just some little bits of information that I'm telling you from looking at the map. Here's the cloud cover. So sky cover, just talking about how much of the sky is covered. So perfectly black dot would be overcast. A perfectly white dot is no cloud cover at all. And then you can see I have my different models on how to tell me what percentages. This is how to read that conditions again. So once again, temperature. This one is dew point. There's symbols in the middle. These symbols tell me what's going on. And so the double dots tell me light rain. The stem, the little stem that tells me where the wind is coming from, can have a little tail on it, and the little tail tells me how fast of a wind speed I'm receiving. And this is done in knots. So 2 long or whole bars, it means that I'm going 10 plus 10 knots, so I'm going 20 knots. If I have a little half bar, and the half bar never touches the end of the tail, so it's on the inside, that's only 5 knots. So these are all ways that I can tell you wind speed. And if there is a flag, it means 50 knots. So I add everything together, just like Roman numerals. So for example, in this one, I have a flag, which is 50, and a half bar, which is 5. So I'm going 55 knots. This one I have let's go down to this one. I have a flag, which is 50. I have a whole bar, which is 10, and I have a half bar, which is 5. So it's 50 plus 10, 60, and 5, 65 knots. Upper level maps, and once again, we've talked about this too, can tell me based on its millibars of pressure, and then I'll actually tell you which height that millibar pressure is occurring at. And there's multiple reasons why we do this. It helps me know if there's a variation in height, which will tell me low and high pressures on the surface, but it'll also help me know where I might find a potential jet stream. For example, if I'm trying to fly in the jet stream or fly out of the jet stream, I'll have to change altitude to stay in the jet stream to fly in it, or change altitude to move out of the jet stream to fly away from it or against it in another direction. And so my maps will be based off of millibars of pressure. And I would say this is an upper level map, for example, at 250 millibars of pressure, which we've seen a lot of when we were talking jet streams. And then on the map itself, they were telling you different kilometers of height that pressure reading would occur at. So these are my different height for that pressure. So this is a 700 millibar map, and it's telling me how high in the atmosphere 700 millibars is occurring. So everything on this line is occurring at 312 km. Once again, upper level maps, just same process as we're going through, and upper level maps. So like I said, I'm going to skip through. Satellite imaging. Satellite imaging comes in 3 basic forms. There is the visual image itself, there is the infrared image, and then there is the water vapor image that comes through. And so I can take these, and so I can see my different satellite imaging as I go through. Radar imaging. This is my pingback or my Doppler system. So here's my radar, and this is a reflectivity map, just showing me how much energy is bouncing off the surface and bouncing back as reflective light. Lift index. This is your thunderstorm index. This is telling me how much updraft I'm receiving, or how much adiabatic process, how unstable is my atmosphere, so how much rising air would I have. And the importance of this is so that I can predict potential thunderstorms, and thunderstorms can have 1, lightning, 2, severe hail, heavy rain, and tornadoes. So it's or and all of those things. And so it's very important to be able to predict these things. And if I live in Tornado Alley, I most certainly want to know what my index is that day, so that I know whether I should be tuning in to a potential danger for my personal safety. This index is known as the K index. So on that note, we have gone through all of our numerical modeling and our forecast modeling, and I will actually pick back up with the next part of our series, which will be our part 3 for module 12, but it's going to be talking about human interaction with weather and how we alter weather conditions, whether on purpose or not on purpose.